Hi guys! So what we're going to do today is a lot of Algebra 2 review. We're just going to spend a little bit of time covering a lot of the stuff you guys saw last year, just to kind of refresh you guys on all these things, and just to recover some real important things that may be coming up soon. So the first thing we're going to review are your parent functions. Now you learned a ton of these in Algebra 2. Some of these you even learned in Algebra 1. So we're just going to go over some of the most common parent functions, what the equation is, and what the graph looks like. Now it is going to be important for you guys to know these. They will come up later, potentially on a quiz. So the first one we're going to look at is the linear parent function, y equals x. Y equals x is just a straight diagonal line that goes through 0, 0. If you can't remember what that line looks like, you can always plot points. Alright, y equals x, if you plug in 1, your y is 1. If you plug in negative 2, your y is negative 2. Then you have the constant function. The constant function is just y equals some number. That's why it's b and not x. It's just some value. And that is just a straight horizontal line with a slope of 0. Now where that's located, that depends on the value of b. So if b was 1, it'd be y equals 1. But that's what your parent function looks like. Then we have the exponential parent function. This is actually one we just did recently. Exponential parent function has a base of a. Alright, so that again, that number could change, but that's our base. So we know this is always going to go through the point 0, 1, because anything to the 0 power is 1. And it always goes through the point 1, comma, the base, or in this case 1a. So I'm just going to graph the line y equals 2 to the x, because that's a pretty common base that you would see. And then if you also remember, that graph has that horizontal asymptote at y equals 0. Alright, now the inverse of the exponential parent function was the log parent function. Actually, I can talk about inverses here in a second. But the log parent function, again, log base a, that one had a vertical asymptote. And it had a vertical asymptote because you couldn't have a negative argument. The points that went through, it always went through 1, 0, no matter what the base is. Then the other point it went through would just be dependent on whatever your base is. But our shape will look something like this. So it is the inverse of the exponential parent function. Alright, going over here we have quadratic. The quadratic parent function is y equals x squared. Y equals x squared is a parabola that goes through 0, 0, negative 1, 1, and 1, 1. If you want to plot a few more points, oh, I missed my dot there. You could plot a few more points if you wanted to. For example, we know this would go through 2, 4. It's another point we would hit, but we're just getting the basic shape here. Square root function. This one has a restricted domain, similar to the log function that also had a restricted domain. The square root parent function is not going to have any negative x values. So the first x value we would plot is 0, 0. Some other points that would be on here would be like 1, 1 or 4, 2, because the square root of those numbers. Alright, the square root of 4 is 2, the square root of 1 is 1. So that graph is going to start at 0, 0. It will touch 0, 0. But it will not continue anywhere past that. So the domain here, we'll look a little bit at domain and range today too. Our domain would be from 0 to infinity. Whereas for log, the domain would be from 0 to infinity with a parenthesis. Because on log it doesn't actually touch 0, for square root it actually does. Alright, then let's look at a couple other parent functions. Once my iPad stops freezing. Alright, so we got a lot over here. And then we got the cubic parent function, y equals x cubed. If you remember the basic shape of that, it's kind of that squiggly line. Looks a little bit like your tangent function did in between. And it went through the point 0, 0, of course. 1, 1. And then this one went much higher up and farther down, because if you were to plug in 2 for an x value, it would go all the way up to 8. So our shape here looked something like that. Cube root, very similar to cubic, but the inverse of it, so it's almost like it's turned on its side. Still 0, 0, still 1, 1, but the difference here is instead of going through 2, 8, this would go through 8, 2. So it's turned like this. Alright, absolute value. Kind of easy to remember because absolute value, the shape looks like a V. It goes through 0, 0, it goes through 1, 1, and in fact this side of your graph looks exactly like y equals x. The difference is the left side is going in the opposite direction. Absolute value, if you remember, basically if you have a negative, it becomes positive. The absolute value of -1 is just 1 because it's the distance that value is away from 0. So you just get rid of that negative to find absolute value. Alright, then we'll review some of our trig functions, sine and cosine. Alright, if you remember, cosine had a highest point of 1 and a low point of -1. Cosine started with that high point on the x-axis, followed by that pattern of middle, low, middle, high. The period here would be 360 or 2 pi, and then your spacing would be based on that. Let's just say that this is 2 pi if it's in radians. So it takes 2 pi to complete a full cycle. Sine parent function, very similar, just shift it over because sine goes through 0, 0. The reason, in case you ever forget, if you plug in 0, the sine of 0 is 0. That's why this one goes through 0, 0, whereas the cosine of 0 is 1. That's why it goes through the high point. So our sine graph would look like this. And again, it would take 2 pi or 360 to complete that full cycle. Alright, rational parent function, we saw 2 of these. The regular rational parent function, 1 over x, that goes through 1, 1 and -1, -1. But the rational parent function had 2 asymptotes. It had a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Then the shape that went through these looked like this, except you should actually touch those points. And then it goes towards those asymptotes. Even power rational, very similar. In fact, it's the exact same for the asymptotes. And it's the exact same on that right side. It's still going to look like this. But because we're squaring that x now, I'm going to get positive y values even with my negative x's. For example, if I plug in -1, 1 over a -1 squared now becomes a positive 1. That's why it flips over like that and they're next to each other. Alright, the last one, you may not have seen this much in Algebra 2. That is the greatest integer function. What the greatest integer function means is that, let's say, for example, you have the number 2.1. Then out of 2.1, the greatest integer you can take out of that value is 2. So you would plot that point at 2. The greatest integer of 3.7 would be 3. Even though you guys are used to rounding up, we're not really rounding here. We're finding the greatest integer that is a part of that number. So what this graph would look like, at 0, it would be 0. And then I'm going to make my spacing a little bigger. I'm going to call this 1, I'm going to call this 2, I'm going to call this 3. What this graph would do is this graph is going to be, if I have 0, 0.1, 0.2, 0.9, any of those values, that's going to round down to 0 for every single value until I get to 1. Once I get to 1, it's an open circle on this function because once I get to 1, it goes back to 1. Now when I'm at 1, 1, 1 is a closed circle, and I'm going to have a straight line until I get to 2. Because every x value in between there, if I have 1.9, the greatest integer would be 1. If I have 1.3, the greatest integer would be 1. Alright, then if I went up here, again, if I went to 3, or 2, 2, 2 would be a closed circle all the way until 3. And this would continue even for the negatives. If this is -1, I would have an open circle, closed circle there, and this would just continue this way. And that's your greatest integer function. You may sometimes see this referred to as the step function because they kind of look like stair steps. It's essentially what you're kind of drawing there. Alright, so those are your parent functions. It's going to be really important for you guys to be familiar with those. It's going to make this next part a little bit easier. It's also just going to make it graphing in general a lot easier for you guys. So the next thing we're going to review are piecewise functions. Now, you may have seen these as well in Algebra 2. These are going to be very important when we start looking at limits. Very, very important. You must be comfortable with piecewise functions. The way piecewise functions work, you have a certain graph that is drawn within a certain domain. So, for example, this graph has 3 different sections, and I have a different function in between each part. So, for example, if x is less than or equal to 0, I'm graphing the function x plus 2. So I'm going to start by graphing that. Usually the easiest way to do this is to start by plugging in the value that's shown. So if I plug in 0, I get 2. So 0, 2 is plotted there. Then it says everything when x is less than or equal to. Since it's or equal to, that's why it's a closed circle. Alright, so it's a closed circle. Then I'll pick an x value that's less than it, like -1. If I plug in -1, I get 1. Now the reason it's helpful to be familiar with your parent functions is it helps you see what this graph is going to look like before you plot a lot of points. I know this is a linear function, so I'm going to have a straight line that continues with that same slope for everything that is less than or equal to 0. Now I move on to the middle part. The middle part here wants when x is greater than 0 and when x is less than 4. So in the area of x values between 0 and 4, so these x values here, I'm going to be graphing the function y equals 2, okay, or h of x equals 2. Well, that's just going to be a straight horizontal line. So everywhere from 0 to 4, and then at 4, I have an open circle. I would also have an open circle here technically, but because the previous line that I graphed was in the exact same point with a closed circle, that circle is filled in. So I can still keep that circle filled in. A closed circle is going to override a, whoops, erased too much. A closed circle is going to override that open circle. So your graph's going to look something like that. Then the last section we'll look at, it says when x is greater than 4, again, not greater than or equal to in this case, just greater than 4, I have my function is the square root of x. So I'm going to start by plugging in 4. The square root of 4 is 2. So when I plug in 4, I have a value of 2. So again, same point I already had. If this was greater than or equal to, then I would plug in that circle. In this case, it's not, so I'm going to leave it open. And again, if you're familiar with your parent function, you can continue this line. If you're not familiar with your parent function, I would pick another x value to plug in, like 5. Or actually, let's pick an easier value than 5. Let's pick 9, because it's easy to find the square root of 9. That gives me 3. So if I go all the way over to 9, then I would go up to 3. And my graph would continue in that pattern. Alright, so piecewise functions are certain functions within these domain restrictions. And we're going to do a lot of practice on this in class. Alright, the last 2 things that we're going to review are compositions and inverses. So compositions is something when we have one function within another function. So let's say, for example, I have the function g of x and f of x. Alright, the first thing I'm going to find is g of f of 3, okay, and if you see it written that way, that's kind of the way you would read that. That is g of f of 3. Another notation you may see that means the exact same thing, you may see g with an open circle like this. Now, you know if you see that closed circle, that means multiply, but an open circle, that's another way of saying composition. Alright, now what this means, we're going to start with the inside part here. We're going to start with just f of 3. Alright, you guys know how to find f of 3. That means I take 3 and I plug it in for x. Since it's f of 3, I plug it into the f equals equation. So when I plug that in, f of 3 becomes 7. So this f of 3 gets replaced with 7. So now I have g of 7. Then to evaluate that, I take 7, I plug it in for x in the g equation, which gives me 7 squared, which is 49. Alright, so let's do a little bit more practice with those compositions. Let's try these next two functions. Let's do f of g of 1. Okay, f of g of 1. So you start with the most inside one. G of 1 means I plug in 1 into the g equation, which gives me 3. Now I'm doing f of 3. Which becomes 1 over 3 minus 1, which is 1/2. Alright, then other way around, g of f of 1. If I plug in 1 for f, what happens? I end up with 1 over 0, which that isn't possible. And if you remember again what this parent function looks like, that means I'm going to have a vertical asymptote at that point. So this function actually is undefined. So it's not interchangeable. They're not necessarily going to be the same thing. G of f of something and f of g of something can be entirely different. Then the last thing we're going to look at is just a composition of a function. Okay, f of g of x, if you look, what's inside here is g of x. This means I'm going to take the g of x function, the x plus 2, and I'm going to plug that in everywhere there's an x in the f function. So that becomes 1 over x plus 2, and then that's going to be minus 1. Now the parentheses in this case, you can add or subtract wherever those parentheses are, so I can just combine those together into x plus 1. If I go the opposite direction, g of f of x, that means I take the f of x function and I plug that in for x into the g function. So that works out to be 1 over x minus 1 plus 2. If you want to write that as one function, you can. You would just need a common denominator. But this actually may be easier to graph because you can see your transformations pretty simply here. I'm going to shift to the right one and up 2. But we're just going to look more about the notation, understanding what that means. Alright, then the last thing we're going to look at are inverses. Alright, so sorry this is a little bit of a longer video, but hopefully this is a lot of review for you guys. Inverses are, we've talked about this when we did our trig inverses, like sine and sine inverse, something like that. To find an inverse, I flip the x and the y. Okay, I flip the x and the y. So for example, this function here, I have 1/2 x cubed minus 4. If I want to find that inverse, algebraically, I switch the x and the y. So I can do x equals 1/2 y cubed minus 4. And then at this point, to see what that function actually looks like, I'm going to try and get that by itself, or get the y by itself. So let's add 4, then multiply by 2, and then finally to get y by itself, I would take the cube root, and that would become the cube root of 2x plus 8. And that would be my inverse. If you were to graph these two graphs would be reflections over the line y equals x. Okay, that's the way our inverses work. They're reflections of each other over y. You also can actually use compositions to double check if two functions are inverses of each other. If two functions are inverses of each other, then f of g of x is going to be the same thing as g of f of x. And what you'll actually get as an answer for those is just x. So let's try this one out and see. I'm going to start by evaluating f of g of x. That means I take the g function. Let's say that this one is g of x. And I plug that in, so I would have 1/2 times my x, which is the cube root of 2x plus 8. That value is cubed minus 4. So we'll simplify this. If I have something to the cube, something cube rooted, and raising that to the third power, that's going to go away. I'm going to end up with just 1/2 times 2x plus 8. So I'm going to end up with x plus 4 minus 4, which gives me just x. Then let's try the opposite way. The opposite way, if I have g of f of x, if I take this function and plug it in for that x, let's see what happens. So I have the cube root of 2 times 1/2 x cubed minus 4. And then still all under that cube root plus 8. So we'll simplify the inside here. I'll distribute that 2. So that gives me x cubed minus 2. I'm sorry, minus 8. Plus 8, which gives me just the cube root of x cubed, which we know is x. So again, using compositions to prove those functions are inverses of each other. All right, now the very last thing, this may be a little bit of new vocabulary for you guys. We're going to talk about whether or not a function is one-to-one. Okay, now a function is one-to-one if every y has exactly one x. So a function, we know every x has one y. Okay, so if a function is one-to-one, every y also has one x. So what that means is that your graph, you're not going to have any repeating x's or any repeating y's. So while a function passed the vertical line test, a function is one-to-one if it also passes the horizontal line test. The horizontal line test. So let's look at an example. If I have the function y equals x squared. All right, y equals x squared is a function. It passes the vertical line test. However, that function is not one-to-one because it doesn't pass the horizontal line test. And if you look, every y doesn't just have one x. For example, the y value of 1, that has two x's. So that is not one-to-one. How this relates to inverses is if a function is one-to-one, then its inverse is also a function. It has an inverse function for the entire graph. Y equals x squared, that inverse would be y equals the square root of x. And while that is the inverse when you work it out algebraically, it's not the inverse for the entire function. It's only that section. This whole part over here doesn't have that inverse. All right, then let's look at one that would be one-to-one. An example of a function that is one-to-one would be y equals 1 over x, the rational parent function. The rational parent function. If you think about what that parent function looks like, at any point on here, every y has exactly one x. So that graph would always pass that horizontal line test. So that function is one-to-one. Alright guys, I know there's a lot of information in here. I think the most important thing for you guys to understand here is to remember what your parent functions look like, what your parent functions are, the equation that goes with each name, and also to be able to graph some of those piecewise functions. And we'll do some practice on that in class.